Okay, here we are. All right. Now, today we're going to be working more on Chapter 8, which is our discussion about interest rates. And we've actually gotten quite a bit of progress done here, but there's still a couple of major topics left to go. So let's see. We left off. I think we're done here. Okay, here we go. So we're going to introduce an important idea. Oh, actually, I think we may have started this one too, but that's right. Let's look at it one more time. The effective rate of interest. All right, so if you go, let's say, to a bank to borrow money or to put your money in your savings account and you're curious about the interest rates that they're paying, you'll discover that they actually are quoting interest rates in two different ways. All right, and so it turns out that they both actually represent the same information, but presented in a different way. In a way, it's like the difference between Celsius and Fahrenheit. If you were told that the temperature was 0 degrees Celsius, and then you were told that it was 32 degrees Fahrenheit, you would realize right away that in both cases, the temperature is right at freezing. The interest rates, what we're trying to determine is how much we're actually earning when we deposit money in the bank, or how much we're paying in interest when we borrow money. Okay, so the two basic types of interest rate quotes, I guess I should say, are the annual percentage rate, APR, and the effective annual rate, which is also known as the EAR. Okay, now both of these numbers tell us something important. But it turns out the effective annual rate is actually the one that's directly relevant, because that's the one that tells you how much you're actually going to pay if you're borrowing, like I said, and how much you're earning if you are lending the money. But the effective annual rate is taken directly from the annual percentage rate. So in other words, you can't have one without the other. And so what we're going to do here, but by the way, let me save this for a second. What we're going to do here is we're going to see how they're related to each other algebraically. All right. So let me just quickly save this. Today's the 21st. All right. So what's the difference between the two? Well, the key difference is this. With the APR, only shows simple interest. All right. So in other words, for example, if the APR is 6%, then you will be paying or receiving, depending on whether you're borrowing or lending, 6% plus the compound interest. All right. So in other words, you're not really paying or lending. The 6% is just the starting point.
My son Tom Holland is playing in Uncharted now.
Really?
You know what Uncharted is, right?
Yeah, I've heard of the game.
All right. Well, that was exciting. All right. Now, what about the EAR? The EAR includes both simple and compound interest. So that's the one that's really the one that you really should care about, because that tells you how much you're actually paying or receiving. Now, by the way, if you own a credit or have a credit card, when you first got it in the mail, they would have sent you a very thick legal document which explains in great detail how this arrangement works. And what they would have been required by law to show you is both the EAR and the APR. Now, credit cards have very high rates of interest to start with. So for a typical credit card, the APR could be, let's say, something really high, like 18%, and the EAR could be even higher, like 19 point, let's say, I'll just make this up, 19.24%. This means that if you don't pay the balance every month, your interest will work out to 19.24% on an annual basis. That's a lot of money. Okay, so this is why you sort of want to push hard to make sure that you're not leaving enormous balances on your credit cards, because the slower you are in paying it back, the more interest it's going to cost you. And it's a lot. I mean, that's a lot of interest. But the key here, the point I'm trying to make here is that the spread between APR and EAR is more than a full percent. And that's because APR is so large. Now, if instead, let's say, right about now for a typical, let's say, car loan, the APR could be, let's say, 6%, while the EAR might be, let's say, 6.24%. You notice the difference now is only 0.24% instead of 1.24%. So what this tells us is that the higher is the APR, the greater is the difference between the APR and the EAR. So you got to keep an eye on that. And you're borrowing. Now, if you're lending, if you're saving, somebody says, listen, you're getting 19.24%, that would be fantastic, but it doesn't work that way. All right, you're not going to get that kind of interest if we're any kind of a savings account or anything along those lines. If you want to make that kind of money, you really have to put your money in something riskier like the stock market. But as far as interest on your accounts, the smaller the APR, as you can see, the smaller will be the spread between the APR and the EAR. And if you're looking at, let's say, a bank account, like a savings or a checking account where the interest rate is really low, the spread between the two could be extremely small, like 0.2% or 0.1% or something like that. Okay, but the most important detail is that between the two of them, the one that really tells you what you need to know is this one. It is derived from the APR, and what separates the two of them is the compounding frequency. All right, so in other words, in order to calculate EAR, you need to know two things, the APR and the compounding frequency. All right, so let's see, where should we go? Trying to make sure, oh, here's one. I think I made this example last time. With a 5-year CD, for example, if you notice the spread between the APR and EAR is really trivial. It's really tiny because it's a very low rate of interest to start with. Okay, so, but having said that, the 1.04% is the amount that you're actually earning. All right, so how do you actually go from one to the other? Well, in most cases, you'll be given the APR and then you'll be asked to calculate the EAR. The APR is the rate the bank is actually quoting you. The EAR is a consequence of that rate plus the compounding frequency. Now, as we saw last time, we looked up in the internet and it told us that most banks compound interest on a daily basis, but some of them do it on a monthly basis. So this will depend on which bank we're looking at. Now, the formula is really not much different, as you can see from down here, from what we're used to. Oh, what happened? What we're used to seeing with our future value formula. And you can see the two formulas are very similar to each other, very similar. The key difference here is that you don't have time. With the EAR and APR relationship, time is not really relevant. What's relevant is the APR and the frequency of compounding. The other difference is that A is a dollar amount and E is an interest rate, which means that it's a percentage. Okay, so, but other than that, the calculations themselves are not that different. So the R in this formula is your APR, the E is your EAR. So if you look at this carefully, N is the number of times a year that the interest is compounded, or in other words, the compounding frequency. So imagine we have the following situation. A borrower takes out a 3-year loan for $10,000. The rate is 6%. The compounding is monthly. So the APR is 6%. But when you take into account the fact that interest is compounded monthly, what is the effective rate of interest? All right, so we plug in the numbers, and you can see that just like with the formula for the future value, you want to simplify this as much as possible. All right, that ratio is equal to 0.005 or 0.5%. So you're taking 1.005 raised to the 12th power, then you subtract the 1, because the 1 represents the return of principal. All we care about is the interest here. So when you do all the math, you'll see that this works out to about 0.0616778, or about 6.16778%. So the spread between the two is about 0.16%, 0.16%. And so that means that if you are in fact borrowing this money, the amount that's actually coming out of your pocket is 6.16778%. Okay, so that's important to know when you borrow the money, how much is it really costing you? Otherwise, you're bound to make the wrong decision. In other words, if you have to decide, can I afford this or not, you have to know how much it's really costing you. All right, so now here's some more examples we can look at. And so let's get some practice here. In fact, you know what I'm going to do? Let me rewrite this equation here. I'll just go steal it from here. And so we're going to assume that a bank offers a 3% APR on its accounts. And these are the 3 different compounding conventions that we might see. And so what we would like to be able to do is calculate the EAR under all 3 of these circumstances. In other words, calculate it once where n equals 1, calculate it again where n equals 2, and then try it again where n equals 4. Okay, now you shouldn't have any trouble with this formula because, like I said, we've seen some very similar ones very recently. So why don't you go ahead and do what you can. Take a couple of minutes and see what you can come up with. All right, so by now you should be ready, at least for the first one. Now, here's an interesting result. If you notice in this case, when you only compound the interest once a year, the EAR and the APR actually end up being the same number. So if you were surprised to see that, don't be, because that's what we should expect. the compounding frequency is once a year. APR is based on the assumption of interest being compounded once a year. So when it really is, the APR and the EAR will actually be the same number. All right, so that one was easy. What about the second one though? Now this is semi-annual compounding, so that's not very often. The spread between them is likely to be very small. And you can see you actually end up with 1.015 squared minus 1. And so that should turn out to be 3.0225%. So it's a very small difference. Now it is a difference though. You can't just ignore it. But you can see it's not a huge amount of money. All right, so if you're keeping your money in the bank, you're happy to know that you're actually getting slightly more interest, but it's not, unless you have $1 million in the bank, it's not going to be a huge amount. All right, so I guess you probably are done with quarterly by now. Let's take a look at it. And you can see this time the amount goes up just a little bit more. Instead of dividing 3% by 2 and raising that to the second power, now we're doing 4. And so now you've got 1.0075 raised to the fourth power minus 1, which is 3.0339%. And again, it's not a big difference, but it is more than what we had with semi-annual compounding. Now, as we keep increasing the frequency, of course, you'd expect this to keep rising, and you'd be correct. So as a challenge, why don't we jump this up to monthly? How about that? Let's try monthly. All right, so why don't you go ahead and work on that? We'll try monthly and see how much of a difference it makes. All right. Now, this one isn't already in the slide, so I'm going to put it together right now. Let's find out what this turns out to be. All right, so this is now 12. This is a 12. All right, and so let's see what that turns out to be. Point 03, 04, 16, let's say. Okay, so it did go up a little bit more, although again, not a whole lot. And here, what you actually have is 1 point. Now, 3% divided by 12 is 0.0025. So this expression is actually 1.0025 minus 1. And that's where, sorry, to the 12th power minus 1. And that's where this comes from. All right, so I'll tell you what, let's complete them. Why don't you go ahead and do daily? Now, use 365 for daily. We don't care if it's a leap year or not. We always use 365. So replace the n with 365 and see what you can come up with. All right, so this one I'd already done. So this one could be rounded up to about, let's say, 3.045. All right, so here's what I'd like to do. Just to have a nice little table to summarize all this information. It's always nice to be able to look at them all together in one place. So let me just quickly put together a little table here. Let's see. All right. So as usual, they've made it green, and I have to find. There you go. All right. So we're going to have the table set up as APR, compounding frequency, and then EAR. Okay. So we've got annual. Oh, wait a minute. Sorry. It's 3.00% APR. Compounding frequency is once a year in the first case. So remember when we did n equals 1. Let's see if I can make this bigger. All right, let's get rid of that background. And that font is just a little too tiny. Oh, now that's a nice font. Okay, here we go. So in this case, oh, no, wait a minute. Okay, that's better. All right, so in the first case, it was 3.0%. And then now these are all three, so I don't have to keep repeating this. Then we did 2, then we did 4. Oh, I need one more. Okay. All right. Then we did 12, and then finally we did daily, which is 365. Okay, so let's go back and revisit these numbers. So in the first case, so the second case, we get 3.0225%. And then we had 3.0339%. And then for monthly, we had 3.0416%. And then for this one, actually I rounded a little. Let me fix this one real fast. It's actually 3.0453. All right, that's better. I want them to be consistent with each other. So 3.0453%. And that's it. So what we can see here in this table is that as I keep increasing the compounding frequency, the EAR is growing and the spread between the two is increasing. But as we continue to increase the number of compounding periods, if you notice, the rate of increase is slowing down. So in other words, as I go from 2 to 4, the increase is 0.0114, but from 12 to 365, it's only 0.0037. So the rate of increase is actually decelerating. And so pretty much this is the limit, is how far you can go with this process. Now, I did mention before, if you tried this all over again with a very high APR, like let's say 12%, you would notice that the gap between APR and EAR would be quite a bit larger. So with small interest rates, the spread between them is usually very small as well. Okay. But with credit cards, for example, the spread can be quite considerable. All right. Now, it just so happens that there's a video about this very topic that we can watch before we go on to the next subject. So let me grab it right now while we're thinking about this. Now, nominal, I just want to mention here, the title of this video is a nominal and effective interest rate. Nominal is another name for APR. All right, so just remember that when you're listening to the video. APR, or watching the video, APR is often known as a nominal rate. EAR, as you can probably guess, is often called simply an effective rate. All right, so let's check this out and see what it's all about. All right, hold on, let me fire this off to you. And let's watch this. Okay, I thought that was kind of interesting. I mean, of course, it's exactly what we've been going over, but she's making some good points. Although, in a bank, as far as I know, maybe it's just the individual states that we live in. I'm pretty sure that you're required to be told both the effective and the nominal rates, so that you know exactly what you're getting into when you borrow money. I don't think they can hide that from you, but they're right though that when you see ads in the newspaper or on the internet, and they say, "Wow, come in here. Our car loans are 6%." That probably is the APR. And then when you get there, they'll explain to you that the actual EAR is maybe 6.12% or something like that. But they can't pretend, they can't actually keep it a secret from you, but they can advertise based on the APR to get your attention and then tell you how much it's really costing you. So, you just have to watch out for that. All right. Anyway, so now there's one more major topic here. Now, all of these examples we've done so far were based on, or had one thing in common. In each case, there was a single amount of money being borrowed or lent. In some circumstances, though, there might be a repeated series of payments or borrowings. For example, here's the classic case of what I'm about to show you. Imagine the following scenario. You buy a lottery ticket, and then by some miracle, you win. Okay. All right, let me just sneak this in here now. Let's say somehow you manage to win a big prize in the lottery. So now the way they're structured, let me just show this in here. All right, suppose that you win a huge prize in a lottery. The official prize is $1 million. Okay, so you figure I'm going to be handed a check for $1 million. Well, typically with these very large prizes, that's not how it works. In many lotteries, the winner does not receive the money right away. Instead, the payments may be stretched out over many years. For example, in this case, you might be told, well, yeah, it's $1 million, but the $1 million prize might be split up into 10 equal pieces so that you would actually receive 100,000 per year for 10 years. Now that's still a wonderful prize. It's not quite the same though, is it? No. In fact, I think you'll agree. I mean, intuitively, you can see why you'd rather have the $1 million all today rather than having to wait 10 years to receive it all. Partially because maybe you wanted to buy something with the money, but also partially because, as it turns out, you can earn more interest if you're saving this money by having it all right away rather than splitting it up over 10 years. Okay, so the winner would be better off having the money right away because he or she could spend it sooner, which is what a lot of the winners do apparently, or B, could earn more interest by investing it immediately instead of being split up over 10 years. Yeah, there's some study out there somewhere, I can't remember, some huge percentage of people who win gigantic lotteries spend it all within like 2 years. And so part of the motivation here for the lottery to hand out the money over 10 years is, well, it saves the lottery a little money, but also it helps prevent people from spending it all very quickly, which a lot of them do apparently. So when we have a structure like this structure of 10 payments of $100,000 each made over 10 years is known as an annuity. Okay, now the word annuity is taken from the Latin word, as you can probably guess. Everything in much of English is based on Latin, of course. Annum, which means yearly. Okay, so there's the whole point of this is that you're getting the same exact payment every year for 10 years. This structure is known as an annuity. Okay. So for some types of situations, instead of having a single sum of money that you're trying to save or invest, you might find yourself saving or investing an annuity. Now, let me show you another example. Suppose that an investor is able to save $25,000 per year for 20 years. To contribute to his retirement savings, let's say. In other words, he's putting away 25 grand a year to go along with the Social Security and its pension and all the rest of that. So they'll have plenty of money to live on when he's retired. This structure of 25,000 per year for 20 years is also an annuity. Okay, so this is because the payments are made once per year and they are all equal to each other. That's the key to the whole thing. The payments are equal to each other. They're made every year and they're equal to each other. So in finance, we call this an annuity. So you can either save in the form of an annuity or you can invest. You can borrow too. In principle, you could actually, let's say, borrow X amount of dollars every year, the same amount. But the bottom line here is that any case where cash flows are exactly the same every year for a fixed number of years is known as an annuity. Okay, now in practice though, these types of structures may take place more frequently. For example, car payments are typically made once a month and are equal to each other. This type of structure is sometimes known as a monthly annuity. So it sounds wrong. I mean, the word annuity means every year, but by calling it a monthly annuity, that means that you are actually paying X dollars every month for so many years. So this also qualifies as an annuity as far as the idea that it's the repeated payment every period, which is in this case a month. And so that can be treated as an annuity as well, even though it's technically a monthly annuity. So when this happens, now, if let's go back here. Suppose that the investor who is saving for his retirement wants to know how much his savings will be worth in 20 years. Okay, he can calculate the future value of each individual cash flow and add them up. Okay, in other words, he can use this formula that we've been using. Oh, for God's sakes, where is it? Here. Wait a minute. This one. Yes, this is our favorite new formula. He can use this formula and apply it to every single one of those cash flows and then simply add them up. But you know what? That's going to take a very long time, isn't it? And there's always a high risk of making mistakes. So if there was another option available to us, we'd probably like to take advantage of it. So it turns out that there is in fact such a formula. So instead, there is a formula that can be used to determine future value of an annuity, which makes it unnecessary to compute the future values of the individual cash flows. Okay, so in other words, for a case like this, you want to use a special formula that's specifically designed to take into account the fact that there are many cash flows instead of one, although they have to be equal to each other, otherwise the formula will not work. Okay, that's an important detail. The formula only works if the cash flows are absolutely identical to each other. If they're not, then you would have to actually go back and calculate them all separately and add them up. But if they're all the same, then we can use a formula. And so I'm about to show to you, and it really, when you think about it and you see it, you might say, well, it's a little bit more complicated than this formula, but not as much as you might think, considering that it can apply to any number of cash flows that you can imagine. All right, so what we're looking at here, of course, is annuities. And let's see, let's jump ahead and look at this formula and see how it compares with the future value of a sum. Okay, so this is the one on the left. This is the new formula. The one on the right is the one that we've been using. The one on the right only applies to a single payment or cash flow, P. This is used if I borrowed P dollars or if I've lent P dollars. Either way, this is only going to happen once. On the left, what happens now is this capital R replaces the P, and it is an indication that this R is repeated multiple times, possibly once a year. So, like I said, you can see the formula on the left is slightly more complicated, but not as much as you might have thought. And so everything else in that formula is already familiar to you. R, for example, is the annual rate of interest, N is the compounding frequency, T is time. Okay, so the only thing you have to watch out for with this formula is you have to be careful with it. It is insanely easy to make mistakes. All right. So, all right, why don't we do this? Why don't we start with a very simple example? In fact, I'll tell you what, let's go back and revisit our saver. Before we go any further, suppose this is just a simple case. Suppose that the investor who is saving $25,000 per year for 20 years can deposit these funds in a bank that pays 5% per year, compounded annually. All right, let's just keep it simple and think in terms of annual compounding. Okay, how much will the investor have in his account in 20 years when he retires? All right, so let's go get the formula and plug in some numbers. And like I said, we're going to do this very, very carefully. This is a case where you really want to simplify it as much as you can. All right, so first of all, let's remind ourselves that our repeated payment is $25,000 a year. The rate of interest is 5%. The money is going to be deposited for 20 years. And N is 1 because it's annual compounding. Okay. So I'm not sure if I have room to do this. So what I would like you to see is that ours, like I said, is 25,000. Lowercase r is 5%. N is 1 for once a year, and T is 20 for 20 years. So what I'm going to do is copy this onto the next slide and substitute some numbers. Give this thing a minute to wake up. All right, here we go. So the repeated payment is 25,000. This is 0.05. This is 1. This is 1 times 20. And then down here, we have 0.05 over 1. Now, the first thing we should be thinking about is simplification. Let's see what we can do to simplify this thing. It won't be hard because of the annual compounding, but let's give it a shot. So clearly, all right, give it a minute to wake up. 0.05 over 1 is just 0.05. So in here, I can replace all this with 1.05. And this exponent is 20. Of course, 1 times 20 is 20. And down here, all I can need is the 0.05. And then what I can do is actually go to my calculator and determine that 1.05 to the 20th power minus 1 is, let's see, 1.05 raised to the 20th minus 1 is 1.6533, let's say, all over 0.05. And that turns out to be, let me just multiply that out. Ooh, that's a lot of money. 826,648.85. So all that saving, oops, that's a little too big. Okay, that'll fit. Beautiful. Okay, so now the interesting thing is the total amount of money that he deposited in this account is only $500,000, and yet he wound up with $826,000. Obviously, he was earning interest along the way. So let me just try something here. There we go. All right, I didn't want that background getting in the way. All right, so in other words, all those payments plus the interest add up to $826,648.85. So what we just did here was calculate the future value of an annuity. And the key detail here again is that the $25,000 payment is being made every year, not just once. All right, if it was just once, then we would be back to this formula. But because it's every year, in this case, we're going to have to use this formula. And of course, that makes things a lot more complicated, but it's useful to have this formula. Now, what about, let's say here's another one. Actually, let me give you a minute to catch up. And then we'll try another one where the compounding frequency is not once a year. All right, so the winner of a lottery will receive $5,000 semi-annually, which means twice a year starting next year, which means the first payment, actually, it's not next year, it's next period, sorry. In other words, you're not going to get the money right away. The first payment will occur in 6 months and will continue for 5 years, so that by the time you're done, you'll end up with 10 payments. Okay. So we're going to put this in a bank that pays an APR of 6%, but it's compounded semi-annually. How much will you have in 5 years? So down here, you see what's called a timeline, which represents the cash flows that you're getting. So in the formula that we were just looking at, this capital R is $5,000. Lowercase r, the interest rate is 6%. T, the time is 5 years. And then finally, N, the semi-annual, the compounding frequency is 2 because it's twice a year. So, all right, this one I've already kind of taken care of. So let's just look at it. And also what I've got on the next slide after that is some tips for implementing this on your calculator without running into trouble. Okay, so let's see how this works out. So I plug in the numbers. Remember, $5,000, 6%, twice a year for 5 years. So if you look down below, you see that you can simplify this a little bit, and you probably should. You could rewrite this as 5,000 times 1.03 to the 10th power minus 1, all divided by 3%. Oops. Now, what I think you should do, and I'll discuss this with you in the next slide, is work on the parentheses first. In other words, what I think you should do is calculate 1.03 to the 10th, whatever that number is, subtract the 1, whatever that result is, multiply by the 5,000, and then finally, when you're done, divide by the 3%. If you try to go from left to right like this, you're going to need a lot of parentheses, and it's going to make your job a lot harder. All right, and so you should end up with $57,319.40. All right, now when you're ready, I'm going to show you the keystrokes that you would need to do this on your Apple calculator. Or any other calculator, really, for that matter, but this one in particular. All right, so what we're going to do is practice this. I hope you have it right in your hands so that you can follow along and make sure you're getting the same results. So assuming that you've done all the simplification and you're down here now, this is what you would do. Following my advice of doing the 1.03 to the 10th first, this is what you would do. All right. So the 1.03 is raised to the 10th equals minus 1 equals. That gives you what's inside the brackets, which is approximately 0.3439. When you multiply that by 5,000 times 5,000 equals, the entire numerator is approximately 1719.58. And then finally, divide by 0.03, divide 0.03 equals, and there you go. All right, so make sure that you're getting the right numbers. If you are, you'll never have any trouble with any of these examples, as long as you did the simplification. And if worse comes to worse, you can round. I mean, if the numbers inside here are very scary, I mean, you can round if you have to. All right, does everybody have that? Excellent. All right, just gonna give you a minute to make sure. There's no need to rush. All right. How about this next one then? If you're ready, the next one says a lottery winner, very similar to the last example we had. A lottery winner is scheduled to receive a prize of 100,000 per year starting next year. By the way, that's a technical detail. The money can't start immediately. If it does, we have to make an adjustment to the formula. So we're going to always assume with an annuity that the first payment starts in the next period. Just like if you buy a car, typically you don't start making your car payments until next month. Or if you buy a house, I mean, there may be a down payment, but normally what you do is you make the first payment the following month. So the payments here are made annually. Again, we're trying to keep it simple. The rate of interest is 6%, compounded annually. If we save all the money, which is a big if, how much money will you have in the bank after you've received all the payments? So that means in our formula, capital R is 100,000. Remember, R means repeated payment. T is 10 for 10 years. N is 1, which means compounded is annual. And it's a 6% rate of interest. And so you end up with what amount? A is what we're looking for. All right, so I'll tell you what, now that we're getting pretty good at this, what I'm going to challenge you to do, let me go grab the formula again. I'm going to challenge you to figure this out on your own. Now, of course, I have the solution right here, but I want to see if you can do this. And let me just repeat these numbers. R is 100,000. T is 10. R is 0.06. And N is 1. So plug in those numbers and let's see what you come up with. Now, by the way, here's a hint. Since you're getting 10 payments of $100,000 each, your answer has to be more than $1 million. All right, if you get something under $1 million, you know something's wrong. Okay. All right, hopefully you're ready. So here's what it looks like. So when you plug in the numbers, the simplification is easy. This is what you're aiming for right here. 100,000 times 1.06 to the 10th power minus 1, all divided by 0.06. Once you got to that point, you still have to be very careful. Like I said, start inside the brackets and work your way out, and you shouldn't have any trouble. So let me show you on the next slide how that would work. This time I broke it up into pieces a little. I like what I've done here. It's a little easier to follow, I think. So in other words, we did what's in the brackets first. And then we did the numerator, and then we get the whole thing. Okay, so what's within the brackets, followed by what's on the numerator, followed by the entire final result. So as we predicted, we ended up with $1,318,079.49, which is good considering that we only deposited $1 million in this account. So our balance is 30% or so higher than it would be if we simply left it in, let's say, under our mattress. Okay. So this is a typical, like I said, large lotteries tend to be structured this way, although you don't hear that advertised. You don't hear it promoted when they tell you, oh my God, Powerball's prize is $100 million right now. I guess they put it in the fine print on the ticket. But I think it's a good idea because, it helps impose some discipline on these people who, like I said, sadly enough, tend to spend all the money fairly quickly. So they don't end up broke or even owing money. So, but having said that, though, if you really meant to invest this money, you're actually not going to do as well as if they had handed you the check right away. And in fact, right now, we're going to see how much of a difference that really could have made here. All right. So imagine that the lottery said, oops, we've changed our approach now. We're going to give you the money right up front. Okay, we've gotten rid of that old system where we pay you an annuity. Instead, we decided that going forward, we're going to give out the prizes right away. So we're going to have the same person receive the money and put the money in the bank for 10 years, 6% annual compounding, but this time they get the money right away. Now, the question is, how much more interest will they earn as a result of this? What's different now is that this is a lump sum payment. So what that means is the formula that we will use is the one that we started out with in this chapter. Our old friend, the future value of a sum formula. So there's, we want to keep everything constant except for the fact that now the money is received right away instead of in 10 equal pieces. All right, so I'm sure you could use some practice. Why don't you plug these numbers into your calculator and find out how much more money this person could have had if the money was paid right off the bat. Okay, let's find out. So if you simplify this, you see that all you're really doing is taking 1.06, raising it to the 10th power, and multiplying it by $1 million. These are the keystrokes. And so you can see, oh man, that made a big difference, didn't it? Between getting your $1 million right away and having it spread out over 10 years, this added another $472,000, $500,000 extra money you could have by getting the money right away. But again, of course, this assumes that the money is being all invested. A lot of lottery winners wish they had done this because they ended up spending it all, but it does make a big difference. Now, having said, just as an aside, having said that, what some states will do is this. They'll say, listen, we know that you're not as well off having to wait 10 years for all the money. So sometimes they'll give you a third option. They'll say, here's what we can do for you. You're supposed to get 100 grand a year for the next 10 years. If you really and truly need money right away, we'll give you 800,000 now, and that'll be the end of it. And some people might take that money because they need it immediately. And others will say, no, that will reduce the amount I can save. So they may say it's up to you, but if you take it all immediately, you don't get the full $1 million. I think, it's good to know that there's another option on the table. Like suppose you need the money right away because you need a new house and you need a new car and you need this and you need that, and there's children's education to pay for and blah, blah, blah. And so you might just say, all right, give me the money now, please. So they will give you that opportunity rather than, all or nothing. Not that most of us will ever have this problem. All right, now here's another good example. This is an investor who's very good at savings. He decides to put $1,000 every quarter, which means every 3 months, into a bank account that pays 4% interest compounded quarterly for 20 years. How much will he have at the end of this time? So I've started the process here for you. I've plugged in the numbers. What I'd like you to do is take it from there and see how much this investor will have in 20 years. Okay, here we go. So what we're going to do is simplify to 1.01 to the 80th power minus 1 all divided by 0.01. So I've broken it up so you can see a little better. The first row represents what's in the brackets. The second row is what happens after I multiply by 1,000. So actually, let me make this a little bolder. There you go. And then when we divide by 0.01, it turns out that this investor will have saved up 121,671.52. All right, so by now you should be getting pretty good at this. You follow the same steps, you'll never have a problem. All right, the key to the whole thing is simplifying it correctly though. Okay, now there's one more thing we can do with this formula. Instead of trying to figure out how much we'll have in the future, what we can do instead is figure out how much do we have to put away every year to reach a certain target. All right, so in other words, we're going to flip this whole thing around and solve not for A, but for R. Algebraically, it's not that difficult to do. All right, so let me show you what I mean by that. Suppose an investor needs to have $100,000 in the bank in 3 years. He's able to earn 3% per year with annual compounding in order when he puts money in the bank. Now we're going to assume that he's going to put X dollars in his bank account every year for the next 3 years with the goal of earning 100,000. How much money does he need to do this? All right, and we're also assuming that it's the same amount. In other words, let's say that the correct amount is, I don't know, $30,000. Then he's going to put $30,000 in the bank each year for 3 years. All right, so in other words, he is basically creating an annuity with his savings. So what we're going to do is look at our formula and we'll say, you know, we know A because that A is actually $100,000. That's what he's aiming for. So what's missing is the R this time. Okay, what we want to know is what R has to be in order to reach our target of A equals $100,000. All right, excellent. Now, so it's a little different, and of course that will affect the keystrokes, but this part in the denominator, which is now the denominator, is the same as the old numerator, so that won't be very difficult. It won't be much different is what I should say. Okay, the order might be a little different. So anyway, so the numbers we have for this problem are A is 100,000, that's our target. R is the rate of interest, 3% per year. N is the compounding frequency once a year. And T is the number of years over which the savings will take place, which is 3. Very good. Now we plug everything in. And as usual, we'll try to simplify it. So that won't be too difficult here. You can see in the numerator, we have $3,000. In the denominator, we have 1.03 to the third power minus 1. Now here, what I've done, because it might be just a little bit simpler, this is a case where parentheses might actually be the quickest way to go. Because you've got a constant in the numerator, but you have to be aware that you're going to need more than one set of parentheses. So if you follow the steps I'm showing you here, you have 3,000 divided by, and in parentheses, 1.03 is raised to the third power minus 1. So be aware that there's 2 sets of parentheses required here. And so the savings each year will be 32,353.04. So don't forget the double parentheses. 2 on the left. Now, the ones on the right are here and here. All right, there's 2. They're just not next to each other. On the left, we have 2 parentheses. The ones on the right that match them off are not necessarily next to each other. But for every left parentheses, we have to have a right parenthesis. All right, don't forget about that. You've got to have one of each. All right, so make sure you can do that. And then we got one more example here. And then that will take care of chapter 8. Let's see, today's Thursday, isn't it? I'll tell you what, I think we're ready for the chapter 8 problem set. Because we've been doing this for a while now, why don't we agree that next Monday, we'll go over the chapter 8 problem set, which is basically all of the stuff we've been doing here. I think I want to get this done while it's still fresh in our memories, because the next chapter is very, very different than this. All right, so let's do this one last example. And this is another figure out the payment problem. Bill Jones wants to buy a $40,000 car, and he can borrow it from the bank. He's going to have to make monthly payments over 6 years. The bank charges 6% interest, but it is compounded monthly. It's going to complicate things. What will be the size of his monthly payments? So based on this formula, A, the amount he's actually going to need is $40,000. R is 6%. 12 is his compounded frequency, and T is 6 years. All right, so we're going to plug them in and show it to you. And of course, you're going to want to simplify all this. Let me just quickly sketch that in here for you. If you do simplify it, you're going to wind up with 40,000 times 0.005. Down here, you're going to have 1.005 to the 72nd power minus 1. And then you can simplify it a little bit more. The product of 40,000 times 0.005 is 200. It's very simply just 200. And then down here, now this, there's nothing we can do about it. We have to figure this out. Whoops. Let me just make this a little neater. All right, so I'll tell you what, why don't you go ahead and try that and see what you get. All right, so that would turn out to be. And again, we'll follow the same procedure, 200 divided by double parentheses, 1.005 raised to the 72nd power, close parentheses, minus 1 equals, don't forget this last parenthesis. So his monthly payments would be $462.92. All right, so I think we're getting pretty good at this. So like I said, there is a problem set in chapter 8. Oh, let me leave that there for a minute. But there is a chapter 8 problem set, which is fairly long, but I think we can finish it in one class. And it covers everything we've done. And now here's some good news for you, though. The second midterm, although you don't want to hear about this just yet, the second midterm is all based on this chapter. It's a fairly short midterm. At least it's not based on a ton of new material. So that one will take place, a little down the road, not too much further in the future, though, because this is what we need to get through that second midterm, finish this chapter, do the chapter 8 problem set, and then there will be a second sample midterm, which will further reinforce all these concepts. And once that's all done, we can have the second midterm and then start studying the material which will ultimately constitute the final, which is chapters 11 and 12. Okay, so we're kind of zooming along now. For it, it seemed to take a while to get to that first midterm, but now all of a sudden the second one is coming up, and then before you know it, it'll be Thanksgiving, and then before you know it again, it'll be Christmas. So we're kind of zooming along now. Sometimes it feels like the semester just got started, but in reality, we're more than halfway done. Okay, so let's do this first. Let's just do one thing at a time. Next Monday, we'll go over the chapter 8 problem set, and then we'll take it from there. Okay, so I hope you, and by the way, of course, I'll post this on Moodle as always, so you can go back and look at the new content here that I've written in here. And if you can do all of these problems, you should have absolutely no trouble whatsoever with anything on the second midterm. Okay, all right, so I will see you all on Monday.
I have a question.
Sure, go ahead.
Will we do like a practice midterm for the
Yes,
second
there
one,
will be
or-
yes, there will, absolutely, just like the
Okay.
last time.
All right, thank you.
Okay.
Yeah, I have another question also. I don't know if you said it in class, but do you know when you're gonna be grading the last exam?
Probably over the weekend. You can probably tell I've been a little bit under.
No, yeah. I'm not rushing. I'm just wondering.
No,
I didn't know if you
but-
sent it out already.
Right, but
Right.
yes, I'm pretty sure they'll be done over the weekend. So
Okay,
yeah,
perfect.
and so yeah, don't it's just gonna the thing is I've got so many of them to do.
No, yeah,
But-
I can imagine.
Yeah, it won't be too much longer.
Okay, thank you.
Okay.
Appreciate that. Take care.
Okay, sure. Anyone else? Okay. All right, so I'll see you all on Monday.